Hello and welcome back. We will continue looking at section 9.1 at hypothesis testing involving two samples. We're looking at telling the difference between two proportions. So here we have 1/4, the proportion of times it's landing heads is 49, another quarter, it looks like the proportion of the heads it's getting is 54 out of 100. So the question is, do the two quarters have different probabilities of landing heads? Can we tell the difference if one is landing heads 49 times and the other is landing heads 54 times? So we went through this in the previous video. You stated our claim that they have different probabilities. Symbolically, this is saying that the proportion of heads for quarter 1 is different from the proportion of heads for quarter 2. Our null and alternative hypotheses. We chose a significance level as 0.1 as opposed to 0.05 or 0.01 because our accuracy is not all that important here, so we can choose a slightly larger probability of making a mistake. Our test statistic, we had this big formula here that involved P1 hat and P2 hat, which are the proportions that we found in the samples. P1 and P2 are the actual proportions for the two quarters, and what we're doing is we're testing whether or not they're equal. And if they are equal, if you subtract them from one another, you get 0. And P bar and Q bar are the pooled statistics here, the pooled parameters. So for P bar, we had 49 and 54 heads flipped on both the quarters, and we flipped them both 100 times. So that's 51.5% of the time we flipped heads, and this is pooled between the two quarters. So our final z-score, the test statistic here, is negative 0.7074, and the area to the left of negative 7.74 was 0.2397, but multiplying this by 2, because we have a two-tailed statistic, a two-tailed test, we get 0.4794, which is bigger than our alpha. So we failed to reject H0, which was that the two probabilities are equal to one another. So if we can't reject that, then we can't say that our two probabilities are different. So essentially, there's not enough evidence to suggest that the probabilities that the quarters turn up heads are different. 49 and 54 are close enough that they could be the same probabilities. So this is using our test statistic, but we can also use confidence intervals to test the difference in proportions. So with this first sentence is essentially the most important one. If P1 and P2 are in fact equal to one another, then we have P1 minus P2 should be equal to 0. Their difference should be 0. So what we'll do is we'll create a confidence interval for P1 minus P2. And there's two situations. We have our confidence interval. So P1 minus P2, we're confident it will be between two numbers. If 0 is inside of this interval somewhere, so maybe there's 0, then we are confident that P1 minus P2 could be 0. So there is a chance that P1 minus P2 could be 0, in which case there's a chance that P1 is equal to P2. So we can't reject the original null hypothesis. The other situation is that 0 might be outside of this interval, maybe to the right or maybe to the left. If it's over here, then we'd say that, since P1 minus P2, we are confident that it is not 0. Well, what that would mean is that we're confident that P1 is not equal to P2, and we can reject our original hypothesis. So let's see this using our previous example. We will need a little bit more information. We've got our formula right here for the error in our confidence interval. So remember that for a confidence interval for proportions is going to be, we're going to look at look at the difference of proportions, and we're going to add a little bit of error and subtract a little bit of error. So this is going to be our upper bound and our lower bound. So we would expect the difference to be between these two values. Again, it should be between what the seen difference is in our samples, the P1 hat minus P2 hat, and then we'll add a little bit of error and we'll subtract a little bit of error. And this is going to be our range here. But what error are we going to add? Well, we have to come up with our critical z-score, just like for confidence intervals that we saw in the previous chapters, and then we'll multiply by this factor here, which has to do with the individual samples that we've seen. So let's apply all of this information. So here we're just going to have the same example. The first quarter we had 49 heads out of 100 flips. Second quarter we had 54 heads out of 100 flips. Our null and alternative hypotheses are still the same. We're still testing whether or not the proportions are equal or not equal. So all of this information we can again write down. So for instance, P1 hat is the proportion of heads for our for the first quarter, which was 49%. But the proportion of failures, in this case tails, is going to be 0.51. For the second quarter that we're flipping, we had 54 out of 100 heads, and the proportion of, in this case, tails is going to be 0.46. We also need N1, the number of flips is just 100, and N2, which is also the number of flips, is going to be also 100, since we flipped our quarters the same amount. So we need to know what our z-score is, what the critical score here, critical z-value is. And in this case, if I draw a picture, this will make it a little bit more sense. We have our normal distribution, and our alpha value. Alpha, remember, was 0.1. So if we split it up and put it on both halves, here this should be 0.05, and this should also be 0.05. So let's find our z value that corresponds to this point. If we come back to StatCrunch, we can go to our calculator and come down to our normal distribution calculator, and the area to the left should be equal to 0.05, which is negative 1.64 if I round that to 5. So I can write that down, 1.645. That's the negative value. The other value on top should be the same. So if I flip this over and I want this to be 0.05, so again this area up here, we get the same value because it's symmetrical, 1.645. So our critical value is 1.645. So our error, which we have the formula up here, is going to be 1.645. That's z, the square root of 0.49 times 0.51 all divided by 100 plus 0.51 times 54 for the second p-value, second probability of success times the second probability of failure, all divided by 100. And our error, after we go through all of this, is going to be 0.116 after we've rounded to 3 decimal places. So our confidence interval for the difference between P1 and P2 is going to be between P1 hat minus P2 hat. This is our best estimate for P1 minus P2. But we're going to add add a little bit of error to the top because there is some uncertainty, and we'll subtract a little bit of error from the bottom. So plugging everything in, P1 minus P2 is going to be between, so P1 is 0.49, P2 is 0.54, so that is negative 0.05, plus some error, and minus some error. So the difference between P1 and P2 should be between these two values. So P1 minus P2 should be between, if I add those together, this is going to be 0.066, and down here this will be negative 0.166. So when we draw our confidence interval, we can see that 0 is in between this negative number, negative negative 0.166, and between 0.66. So 0 will be about there. So because 0 is inside of this confidence interval, we will fail to reject P1 being equal to P2, because P1 could be equal to P2. There's nothing saying that, so our evidence suggests that if we want to be 90% confident, it could be the case that P1 is equal to P2, that P1 minus P2 could be equal to 0. And since we failed to reject this, it could be the case that P1 is equal to P2, and our conclusion would be that we can't say that they're different. There is not enough evidence to support P1 not being equal to P2, so we get the same conclusion that we did using our original statistics, our original p-value method of solving this. Now, in StatCrunch, we can actually perform both of these hypothesis tests very easily. So if we come to StatCrunch, and we're looking at comparing proportions, and we have two samples, and what we have is the summary data. We don't have the individual coin flips. We just know that we had 49 out of 100 and 54 out of 100. So when this comes up, it'll ask for the number of successes, the number of observations for both of these. So for the first coin, we flipped that 100 times and got 49 heads. The second coin, we flipped that 54 times out of 100 heads. And if we're doing our original hypothesis test, yes, we were testing whether or not P1 is equal to P2, as in their difference is 0. And the alternative hypothesis was that they are simply different from one another. So P1 is not equal to P2, as in their difference is not 0. And then I can make a p-value plot just to visualize this a little bit better. And in doing so, we can compute. And we have the same p-value that we had before. Again, it lists the counts for both, for how many successes we saw, how many times we flipped both quarters. Our z-score and the p-value are exactly the same that we had calculated before. 0.4794, so there's a little bit of rounding, and negative 0.7074. So again, since the p-value is bigger than alpha, we can't reject our null hypothesis. So all this data value can be very easily computed. You saw when I entered that in. And then this is, again, because we have the two-tailed test, we're looking at the area to the left and to the right of our z-score. So that's pretty big. And then very quickly, what I can do is the same thing. So we can go to proportion statistics, go to two-sample, and summary again, inputting the same information, but instead of doing a hypothesis test, we can compute a confidence interval. So instead of doing the hypothesis test, we can do a confidence interval. Since alpha was 0.1, meaning 10%, our confidence is going to be 0.9, and we can compute our confidence interval, and we get the same upper and lower bounds, which contain 0, as is shown in this nice picture.